All right, it's time. Let's continue. So we were talking about SIR, modal, epidemic. People who got infected, people who recover, okay, and people who are susceptible at the beginning. We have these three group of people. Okay. Then it turns out the last one only depends on I, and the first two does not depend on the last one. So we can decouple them to just treat the first two equations as an IS equation. Okay. We solve it using a computer provided by Python, or you can do it by Void Euler, whatever. Okay. We'll end up with several interesting observations. Number one, for ST, no matter how you do it, basically this one just drop down. Okay, starting from some point, you just drop, and eventually have a steady solution. This is for ST. For RT, it's pretty straightforward. No matter what you do, you start from no people recover, they are infected or susceptible. Starting from the place, you recover at a rate of beta, and eventually you have something like that. Okay, so susceptible and recover, it's pretty easy. Susceptible people drop, recovery goes up, and eventually these two sum together equal to 100% because there's nobody who got infected anymore. Now for the infected, we do have two possibilities. First possibility, it goes on like this. Notice, eventually it becomes 0. Okay, number two, this one just goes drop down all the time. Okay, there's a second possibility. That is, this one first go up a little bit, and then they drop down. Eventually also goes to 0. We call this case no pandemic. Because basically, the moment you find people who are infected, they just drop quickly to 0. We call the green one with a pandemic. So at first, the people who got infected is going to increase, okay? But eventually they all drop down to 0. Okay. Certainly we find that this has something to do with alpha and beta. Okay, a big alpha, easy to get infected, slow to recovery, certainly is more likely to give us something which is similar to green. Okay. Second, we said, even though both eventually goes to 0, you have two important factors to consider in real world. Number one, the green goes to 0 slowly, which means if people die when they're infected, say 2 weeks or 2 months, they're going to die. The longer they are in infected status, the worse. Second, maybe there is a threshold of population you can treat with your medical system. So certainly we want to have the no pandemic case. Okay, because we don't want the medical system to break down. If you let the pandemic happen, it's possible that at the peak, the medical system break down, and then after that, the fatal rate becomes super high, simply because nobody gets treated. Not enough people get treated. Okay, so several observations. Number one, we have two cases, no pandemic and a pandemic. Depends on alpha and beta. We want to know what's going on. Okay. The second thing, of course, we have the face portrait. Roughly look like this. Yeah, probably. My drawing is bad, but hopefully you still remember what's there. Roughly we have something like that. S and I. Okay, so basically this one tells you eventually your I drop to 0. S decrease. Meanwhile, all of them actually share the same place where you have the maximum of I. Okay, we wonder where that thing is and how to connect all these ideas together. All right. For pandemic and no pandemic, and for face portrait, where is this straight line? Now we're introduced the two things. The first one is face portrait. We want to know where is this green line and what does it imply? Moreover, what is the solution? Okay. If you think about it, we do have the first and second equation. Negative alpha Si di over dt alpha Si plus actually minus beta I. Well, you can solve each one as a system, and then you eventually have a ST and IT. That's what we mean by solution system. Meanwhile, if you're just thinking about face portrait, actually you don't care about the relation between I and T and S and T. You care more about, because it's in SI plane, you care more about the direct relationship between S and I. Sounds good? For that purpose, what you can do is actually you can simply use the second one divided by the first one and see what you got. Well, you got di over ds, which is basically I as a function of S. That's the direct relationship between I and S. Moreover, it's actually pretty nice to write down. Basically, everybody divided by alpha I. The first term becomes -1. The second term becomes plus beta over alpha times 1 over S. So instead of system, you actually have a differential equation with respect to I and S. That's the beauty of autonomous system. There's no T. All right. So question 1, remember your face portrait? Something like that. You wonder where this is, which is horizontal. Okay. Now judging by what we just did, that's basically where di over ds equal to 0. That's what we mean by horizontal, not in IT plane or ST plane. It's in IS plane. So you just set this one to be 0. It's very easy to see S equals alpha over beta. So this one here is going to be alpha over beta. That simply means if you increase alpha, the whole thing will actually shift to the right and to be more like this. Because your alpha is going to become bigger if you keep beta. That means the quicker you actually reach the maximum of your I infected. Sounds good. That's another interesting indicator. That is also, this one tells you when are you going to have a pandemic or not having a pandemic, because this is where alpha over beta is. Okay. So what do you mean by you have a pandemic? That means your I actually increase before you decrease. That means you have something like this. Pandemic. Because you first increase, right? And then you decrease. However, for no pandemic, basically you just have this case. Because your peak is already here and you pass the peak. So from now on, you can only go down. Therefore, it's more like this. No pandemic. So do you have pandemic or not? It really depends on, are you on the left of alpha over beta? No pandemic. Or are you on the right of alpha over beta? That means you do have a pandemic because you first go down to go to the maximum, and then you'll go up to maximum, then you go down. And when I say left or right, I mean your initial value as 0. Thanks to what we just computed. This is working. Sounds good? Okay, so this number is very special. From here, you also see that it's actually not about alpha or beta. It's actually about the ratio between alpha and beta. For example, a 0.2 infection rate divided by 0.1 recovery rate will produce some dynamic which is similar to 0.4 divided by 0.2, even though both are higher. But the key factor here is actually the ratio between them. Okay, that's the first one. Pretty nice. Well, that's what information we get from doing this 2 divided by 1 case. Is there anything else we can get from here? Well, do you realize this one is actually solvable? If I change this to y and t, you basically have dy over dt equals -1 plus beta over alpha times 1 over t. Do you realize it's actually a solvable differential equation? That means you can solve it and get I as a function of s, which is not t anymore. So what you can do is you can solve it. Well, how to do that? It's linear, so di over ds. Do I want to do that? I probably want to do. Okay. Di over ds minus beta over alpha 1 over s is -1. Okay. You can do separable. Is separable easier? Separable is not easier, is it? Hold on, what am I doing? Yes. Okay. Integrating factor. I think it should be doable by separable equation, but in my notes, I did integrating factor. So let's just do that. 3 times mu, okay, di over ds, minus mu beta alpha is s. Yeah, that's why I think. That's, hold on, what am I doing? It's separable. I'm just stupid. Okay. We can do the integration already. Okay, 3 Of course, we do the integration with respect to ds. So far, this is the general solution. To figure out what C is, we just need the initial value. Okay. Well, it really depends on how you collect the data, but what you can do is, initially, we should know normally when the pandemic starts, S is roughly 1. Sometimes it's 0.99, which means all the population are susceptible, and your infected is almost 0. That means you only have a small part which get, how to say, infected. With this assumption, we can basically conclude I, S equals 1 equals 0. Technically, it's not equal, it's roughly equal. But approximately, we just set it to be equal. Okay. Then roughly we can plug in and solve this. -1 plus 1, C equals 1. So together, okay, note S is positive. This will be the solution, roughly, in this IS plane. Moreover, this only works for as this initial condition. So if the initial condition is way far away from this, you cannot use this approximation. So this will be the formula you'll see a lot when you Google for pandemic, which give you the relationship between the infected and the susceptible. Okay, basically what they got is actually they got it by dividing the two equations to get an IS differential equation compared to the STIT. Sounds good? Okay. This is now interesting because this is actually no better than if we just solve each one separately. But the trick we did here is worth mentioning because it's used a lot in real life. That is, if you have two things, one is a differential equation of t, the other one is a differential equation of t. And if they're autonomous, that means this one does not have anything to do with t. It's just FSI, GSI. Then you could always solve it in two different ways. The first one is you have a ST, you have a IT. Yeah, let's just use this case, SD and the IT. IT. Okay. In the T, actually, let me write them separately. You can write it in TS plane. You solve it. and then ti plane and solve it separately. That's certainly one way of doing it. Solving it as a system. Or you can take another approach. That is dividing them. You got something with di over ds or ds over di, depending on whichever way you want. The good news is this one is going to give you some function, which is g over f, which only depends on s and I. So this one itself is a differential equation, which happened in the SI plane, not t, no t anymore. And you can solve it directly to get this. Okay. That is called solving the differential equation in the phase plane directly. Similar to the one we just did for pandemic. Which one's better? I mean, for the second case, you only solve one equation compared to two. So the second one is better, but the second one only gives you some information on the phase plane, not the original function, only the phase plane. Okay, so depending on what you want, you can save some trouble and do this. That's a very popular technique when you try to learn physics and solve differential equations. A lot of times people do operations directly on the phase plane. Okay. And usually when people do it, they do approximations. Like the thing we just did. We only know I0 and S0. We do not know the initial condition for this IS thing, so we just made a guess. We guessed I1 is roughly 0. That's not real, that's an approximation. Okay? So when you do things directly in phase plane, approximation is usually used because you don't have the direct access to the information. Sounds good? All right. Push one more step. What is really happening? What is really happening is you technically have three variables. You have S, you have I, you have T. Okay, so if you really solve this differential system, you thought you have only two variables, S and I, right? But you actually have a third variable, which is T. So what you solve is actually in space-time, a curve. That's where the real solution lies. Now you notice what we just did. We basically just did the projection of this real solution to the SI plane, ST plane, and IT plane. So every single one of them is actually part of the information. The real information lies in the original high-dimensional, three-dimensional curve. Make sense to everybody? Okay, so that's actually the beauty of solving differential equations, which involves time, usually the third variable. If you push into high dimension, now you notice if you want to study S and I separately, you can project them all the way to the plane with respect to T. Then the phase plane is actually whatever left, okay, for the projections. In this case, it's actually on the original horizontal XY plane. If you notice, this is the SI plane. And when you do that, what you get is actually the relationship between the variables directly without time. Okay, so this is more for interactions between multiple variables, in this case, S and I. So these two give you separate solutions if you want to see how they evolve directly. But this phase plane actually give you how they co-evolve together, which is the interaction of them. When I goes up, S goes down. When S goes up, I goes down. You want to study those kind of relationships? Phase plane is the best choice. Okay, but they all come from the same original information. All right. Any questions so far? The way to solve this one is not too impressive. Okay, the more impressive part is actually this trick, which you may use later in physics all the time when you study the interactions between two quantities you care about. Okay, it's basically high dimensional projected to phase plane. All right, number 3, pandemic or no pandemic? We just want to quickly do the assessment. Okay. Basically, you just wonder, do you have this? Or do you have that? Okay. And remember, this is in IT plane. So basically, you just care about your I, d over dt. Minus beta I. And we can easily do a thing here. Actually, let's put I here. All right. How do you tell the difference between the two things? Well, for this case, my derivative is negative from t equals 0. For this case, my derivative is positive from t equal to 0. And eventually it goes to negative once I hit the peak, of course. So really it's nothing, just try to see if this one is bigger or less than 0. Okay. If this one is less than 0, that means alpha s minus beta. I is always positive, less than 0. That means your s should be bigger than beta over alpha. Hold on. Beta over alpha. In this case, which basically means S0 is less than beta over alpha. You can verify by yourself. think I made a mistake here. Where is it? This should be beta or alpha. All right. Now we can connect everything together. First is the no pandemic case. Number one, your graph goes like that. T, I. This corresponds to S0 is less than beta over alpha. Okay. Meanwhile, on your phase plane, this is beta over alpha. This basically means if you start of your S less than that, you always go down. Why? Because your peak is here. Okay. For pandemic case, yep, correspond to S0 is bigger than beta over alpha. Now for phase plane, beta over alpha. This basically means you start from here. So of course you go up a little bit until you hit the peak, and then you go down. Sounds good? All right. So from here, you can see pandemic or not totally depends on this ratio. Therefore, it deserves a name. We give this a name, R naught number. Number. Which is defined by this ratio, but we define it by alpha over beta, not the other way around. Because we're trying to use this one to indicate risk. So the bigger the alpha, the bigger the risk, because alpha is the infection rate. Okay. Then you can see this corresponds to 1 over R naught. This corresponds to 1 over R naught. And this number here is actually 1 over R naught. Okay. Everything works except for we define R naught to be the reciprocal. And that is because we want it to be the risk. Okay. Sounds good? Now, how do we control pandemic? We don't want pandemic to happen. For example, we already got a disease. We know the infection rate is 0.2. We do know the recovery rate is 0.1, which gives us an R naught number, which is 0.2, 0.1, which is 2. So this one is almost like dangerous. How dangerous? Level 2, roughly. All right. Do we have a pandemic? Depends on how many people at the beginning are susceptible. If S0 is less than 1 over R naught, which is the beta over alpha thing we just did, which is 1 over 2, no pandemic. If S0 is bigger than 1 over R naught, pandemic. So we're looking at the threshold. That is 50%. Still okay? Now, let's say if we have 100%, which means everybody is vulnerable to the disease, are we going to have a pandemic? For sure. Okay. Then how do you do something to stop the pandemic from happening? You need to reduce this one to 50% and less. How do you do that? Vaccine. That means if you have 200 million people in the United States and you got a disease which is R naught equals 2, you need to make sure less than 50% of the people are vulnerable, which means you need to give vaccine to at least half the population, which is 100 million people. Make sense here? Okay, the bigger the R naught, the more dangerous the disease, the more people you need to give vaccine to make sure the fewer people that is susceptible to this disease. Now for flu, for example, maybe flu has something which is roughly 0.1, okay, or something like that. R naught number, that can't be 0.1. That's too ideal. Let's say for flu, I don't know, let's make up something up, 1.1 R naught. Which means you have pandemic if S0 is bigger than 1 over 1.1, which is roughly 90%. Then what you need to do is just make sure that you give vaccine to 10% of the people. Do a little bit better, 11% of the people, then the whole population is safe. Then you're safe. Okay, so calculating the R naught number of a disease basically give you instruction on how many people, how much of the population has to be injected with the vaccine. That's pretty neat. Sounds good. Which disease is more deadly? You simply just compare their R naught number. The one with the bigger R naught number, it's more deadly in terms of public health pandemic level. Okay. You can also give them different levels. Below certain threshold, you call it pandemic. Above certain threshold, you call it epidemic. Okay. You really have all the studies of doing this. Of course, now our world is connected. You can think about how we can change this thing. For example, for COVID-19, what's going on? Well, that thing certainly has a big R naught number. It's very easy to get infected. It's very hard to recover. So you probably need to give people back vaccine. Sounds good. But if you cannot give people vaccine now, what can you do? Well, you need to somehow control the R0 number. You need to control this. You need to make sure this one goes down until the vaccine comes. How can you do that? Well, number one, you save people by increasing beta. That is, you treat people with all the ventilations, all the good treatments you can give people in order to treat them. Or you need to dramatically reduce alpha, which is the chance that people get infected with the same population. That's why we need lockdown. That's why you guys are staying at home instead of going to the classroom. Sounds good? So for now, we don't have vaccine. We're desperately trying to control the R0 number by increasing beta, providing a lot of treatments, and decreasing alpha by locking people down and stopping the connection. Don't go to the bar, don't travel, things like that. Plus you have multi-nation, you have multi-continent, you have airplanes, you have traveling. It's gonna be very, very complicated if you really want to apply this one in real life. So I give you a project after the exam. You can play with it. Certainly it won't be perfect. And when you do that, you will realize how hard it is to use this one to actually work something out as a menu to tell people, if you follow this, we're safe. Okay, there are so many other things you should consider. In general, it's hard. But however, CDC and the WHO is trying their best to use the model to predict. Okay, and there is which is sad, but there's a lot of research going on. Because of the pandemic, we publish a lot, simply because now we have a really nice case to verify which model works better. Sadly, that's the case. Okay, that's all the basic of SIR model, a very popular model for epidemics and pandemics, of course. Any questions so far? A really interesting question you should think about from now on is, how can you use this one to model something else other than pandemic? For example, Twitter. Okay, you put some comments on Twitter. People is going to look at it. They're going to retweet it. Okay, it's almost like a pandemic spread, pandemic spread of information. So this model actually can be used to model the spread of rumors, message on Twitter, social media, and people use a lot of these models in this way. Second, of course, on graphics, on internet, because you know the connections between different machines so well, you can actually very accurately estimate alpha and beta because you know how they interact with each other. You can find all the visits and the information and logs between the machines who are connected or not. So this one can be combined with graph theory. Once you put these two together, it becomes pretty powerful. Okay, now you have people are connected. Some of them are connected. Some of them are not connected. Okay, then there's a chance they get infected, or these two people can only get infected through this connection, but not between them. You have different clusters and things like that. Okay, it will become more complicated, but that will be super interesting to think about. By the way, you can also spread fake information in this way if you want, computer virus in this way, or if you want to destroy a certain kind of, network, you can actually figure out which part is the easiest one to attack, such that you can completely block out the spread of a certain kind of information. That can be used in war. Cool. Oh, number 4. Some other models modified SIR. You just simply add some terms. This is the SIR. Skeleton. Okay, I better make a copy. Well, the first thing you can add in is vital information. You didn't assume the population is changing, right? For example, you didn't assume that people are having babies and people die from just, aging. You can certainly give people vital information. Which means birth and death. Okay, so just minus S plus I plus R times the death rate. And depends on if the newborn baby is immune to the disease. You can either say you can add more information because you got more people who become susceptible. So alpha. So this will be the death. This will be the baby, newborn, with some, probably not alpha, gamma, birth rate, death rate. You can even do a logistic growth here if you want. It's pretty easy to do. And then, of course, people here die at a natural rate, and people here die at a natural rate. What I should here should just be S. Okay. Other people will be calculated elsewhere. That's one possibility. Okay. Second possibility. Note what we have here. We basically say if you recover from the pandemic, you're all set. You will never get infected again. So R only grow and S only goes down, right? It's possible that you lose immunity. That means your recovered people will gradually become susceptible again. In this way, your S will not be always decreasing. It may increase at a certain time. If that is pretty hard to take, at least you can think about mutations of the virus, right? If you are immune to the old one, but if the flu mutate to a new type of flu, and then 10% of the people who has been infected by the old flu before will be susceptible to this new one, then you can use this model with loss of immunity or mutations. Sounds good? All right. Some other thing called SERAR. You know SIR. S are the people who can get, I are the people who get infected, and R is the people who recovered. E here stands for exposed. Not infected yet, but they're exposed. Then of course you have exposed rate. And of all the exposed people, you have an infection rate. Okay. Certainly, you need to add in something which is dE over dt. You need to modify something here in order to consider the E. E probably happens between S and I. It's really long for me to write it here, so I will just leave you to Google. It's pretty easy. Okay, so Google it. I had it on my notes. It's just I need to erase this and write. You read it. It's really easy to read. Now think about COVID-19. If you pay attention to the news, they tell you like after you get exposed to the virus, it will take you 2 weeks to show some symptoms or get infected. And it's possible that you get exposed but not infected. Sounds good. So this E here is more for the delay of time from you get exposed to the virus to when you actually show the symptoms. So I would say this will be the more appropriate one for COVID-19, since we have that 2-week period. Okay. After that, you can add a lot of things you want to model. You can add, for example, traveling frequencies, add it to somewhere. It affects the infection rate, maybe the susceptible rate. You want to add in, immigrations, border openings, lockdowns, and things like that. So you can keep adding things you want. Of course, once that thing becomes more complicated, you cannot just define R naught number. You maybe have to define R S naught number, I naught number, whatever number you define for your model. Sounds good? So in real life, SIR just give you a framework, but really, which one to use? And can you add some personal customized component to it? Totally. Okay, so that's just the framework to start with. Think about what you can do with it. It's pretty, I've known many people who does SIR for life. It's just their life career. Keep adding new stuff to the new pandemics. So that's a very rich topic. Okay, up to now, chapter 2 is over. We will start chapter 3 next week. Any question before today's lecture is over?